When you tap a button on your phone to buy something, you expect a heavy cardboard box to appear on your porch 24 hours later. It feels like an instant, purely digital transaction. But to make next-day delivery work at a national scale, there is no digital magic involved. You're actually triggering one of the most highly pressurized, high-speed physical machines ever built, designed to process up to 1 million identical clicks every single night. The main problem these facilities face isn't having the inventory in stock. The problem is distance, physics, and time. And for decades, the logic of storing things relied almost entirely on human speed. Look at this warehouse map. In a traditional setup, inventory sat still on static shelves. If you needed a toothbrush, you walked to that aisle. A human worker picking orders might walk up to 15 miles in a single shift. They spent 80% of their time just moving between shelves, and only 20% actually retrieving products. If a massive wave of orders drops into the system, and each requires a 5-minute walk to retrieve, those intervals massively compound. The warehouse floor immediately floods with unfulfilled orders, and the dispatch trucks leave empty. You cannot physically offer next-day delivery to millions of people if your logistical engine is limited to the walking speed of a human being, and the math simply does not work. Engineers realized they couldn't hire more people to walk faster. They had to completely invert the architecture of the building. Instead of sending the human to the shelf, they figured out how to send the shelf to the human. Inside a modern fulfillment center, the vast majority of the floor space is entirely fenced off from humans. In this zone, thousands of autonomous mobile robots zip across an unmarked grid, carrying towering yellow storage pods that weigh up to 1,000 pounds each. This diagram illustrates how they navigate. These robots don't use cameras to see like a self-driving car. Instead, they use an inverted digital map. As the unit drives, a downward-facing scanner constantly reads a floor grid of highly precise QR codes spaced inches apart, giving the machine its exact location down to the millimeter. Because a dead robot in a busy intersection would instantly become a physical boulder and block traffic, these units self-monitor. When a charge drops below a critical threshold, the robot requests clearance and smoothly routes itself out of the swarm to a perimeter charger, while a fully charged unit seamlessly takes its place. The real hidden engine here is the central routing algorithm, acting as an industrial air traffic controller. Because thousands of units move simultaneously, the server constantly calculates right-of-way, ensuring that 2,000-pound pods crossing a high-speed intersection clear each other by a matter of inches without colliding. The worker stands in one highly ergonomic spot, and the entire warehouse dynamically rearranges itself to bring the required inventory directly to their hands. But if you look closely at the shelves these robots carry, you won't find an aisle set aside for books or electronics, a best-selling novel crammed next to a dog toy, and a bottle of shampoo. It looks like a randomized mess, but it is a brilliant mathematical strategy called chaotic storage. This comparison shows why organization fails at scale. Imagine if the warehouse kept all dog food in one zone. If a sudden surge of orders came in for that food, hundreds of robots would converge on that single coordinate, creating an immediate, catastrophic traffic jam. By deliberately scattering identical items randomly across the grid, the system guarantees there is always a pod nearby, ready to be grabbed by the closest available robot. This chaotic ecosystem sustains itself seamlessly. When new inventory arrives, a worker simply looks for any empty cubic space on a pod, shoves the item in, and scans it. In that fraction of a second, the physical item is permanently bonded to the digital coordinate of that specific pod bin in the central database. Getting the item off the shelf is an operational triumph, but before it leaves the building, it encounters another massive physical bottleneck: packaging. In the past, human packers guessed which box size to use, frequently grabbing a box that was slightly too large and filling the empty space with plastic air pillows. In logistics, shipping empty air is a catastrophic waste. A semi-truck will almost always cube out before it weighs out. This means the trailer runs out of physical volume long before it hits its maximum highway weight limit. To solve this, the warehouse relies on dimensional algorithms. The computer knows the exact millimeter dimensions of your item and dictates the precise box size the human packer must use. Some advanced facilities bypass standard boxes entirely, using auto-boxing machines that custom cut, fold, and glue corrugated cardboard perfectly wrapped around the item in real time. By algorithmically eliminating the empty air inside the box, the warehouse crams up to 20% more packages into every single departing truck, keeping hundreds of unnecessary vehicles off the highway every day. Once perfectly packaged, the final hidden system takes over. The facility has to accurately route hundreds of thousands of individual boxes into the correct regional shipping trucks, using a mechanical river of belts spanning several miles. As your box moves down the main transport belt at speeds exceeding hundreds of feet per minute, it passes through enclosed scanning tunnels. These archways are rigged with high-speed, multi-angle cameras that capture all 6 sides of the box simultaneously, decoding the tracking barcode in milliseconds. This animation demonstrates a critical failsafe called SLAM. The box gets tracked and dynamically weighed while still moving down the belt. The system compares the actual physical weight of the box to the theoretical weight of the items that should be inside. If it is even an ounce too heavy, a diverter arm instantly kicks the salty box off the main line. A fraction of a second later, the verified boxes use their scanned data to actuate a physical mechanism further down the line. A pneumatic shoe fires to kick your specific box off the main transport and down a spiraling chute directly into a waiting semi-truck. The timing must be flawless. A tenth of a second too late, and the box goes to the wrong city. This relentless, pressurized mechanical routing stands in complete contrast to the quiet, static environment of a residential neighborhood. A cardboard box sitting peacefully on your front steps is the furthest thing from a simple digital transaction. It is the final physical output of an invisible mechanical swarm, a massive industrial machine that successfully fought off time, weight, and total operational gridlock just to save you a trip to the store.